All right, let's look at the electrical resonance. All right, so we have a RLC circuit again, and we're going to use the sine curve to simulate the power source. All right, so E of t is equal to E0 sine of omega t. All right, so when we take the derivative of that, we get E prime of t is equal to omega E0 cosine of omega t. All right, so we have this the differential equation for the current Li double prime plus Ri prime plus 1 over Ci is equal to E prime, which is omega E0 cosine of omega t. And remember that we have this mass spring dashpot system, which has a very similar equation. So I'm going to just pop that up. All right. So this is the differential equation and steady periodic solution. All right. So you can see that we can kind of match things up. For example, the L is going to be matched to M, right? Then we're going to match, R to C, right? Then we have 1 over C to K, right? Then next one is here, omega E0 to F0, right? So since we already have amplitude function f of 0 over square root of k minus m omega squared quantity squared plus cw quantity squared for the solution of the mechanical system. So what we can do is we can use that formula, turn it into the formula for the solution for the circuit. So it's I'm going to say I steady periodic solution, right? It's going to be here's the amplitude function C of omega. Then you have a cosine of omega t minus phase angle alpha, right? So where, all right, let's try to rewrite this. All right, so we're going to have a C of omega is equal to, right? So let's just match everything up. All right, F0 is corresponding to omega E0, right? Then we have a square root, right? And a K is 1 over C. So we have 1 over C here minus M is L. So you have a L omega squared plus C is R. So R omega squared. All right, to make it look a little bit nicer, I'm going to actually divide top and bottom by omega. So I'm going to just do 1 over omega here and a 1 over omega. All right, then what happens is, let's see, on top, you're going to have just E0, right? Because we can cancel out the omega here and omega on the bottom, right? Then we're going to actually have to put 1 over omega inside the square root. So we still have square root here, right? So inside 1 over omega becomes 1 over omega squared. So if you put that inside square, so it's going to be simply 1 over omega c minus, we have to divide by omega, so it's going to be L omega squared plus, right, divide by omega squared cancel out, so you're just going to get R squared. All right, and since it gets squared, you can actually switch terms. So I guess the textbook might have written it this way, but which is exactly the same thing. So E sub 0, E0 on top, Then you have a square root. Right? Then we have, we write it as actually omega L minus 1 over omega C squared. Right? So I've just switched these two terms. It doesn't really make any difference because it gets squared. So it's exactly the same thing. And then plus R squared. All right? There's some terminology, and here's the new terminology here. The denominator, this expression, is usually, we can call it Z, and this is called the impedance. Right? And if you look at the, if you think of the current I, so and we're talking about this is just the amplitude of I. So amplitude of current I, so let's call it I0, can be written as E0 over this impedance Z, right? And if you compare that with the Ohm's law, which goes something like this, you have I is equal to the voltage divided by R. So resistance. So this is the Ohm's law. And the impedance Z actually, it corresponds to the resistance R. Right? So you can think of Z as a kind of analogous to a resistance in the Ohm's law. Right? But this is called impedance. Another one is this inside here, this quantity right here. This guy is called the, we usually call this S, and this is called the reactance. Right? It's just a name. All right. And what we want to do is, since we know the amplitude of the solution ISP of T, and what we want to do is we want to find the frequency omega so that amplitude is the largest. And in this case, it's very easy to make this the largest possible. All right, so E0, there's nothing we can do about that. And resistance R is fixed. Right? The only thing we can do is this guy right here. Right? To make this amplitude as large as possible, the best you can do is this reactance being equal to 0. Because since this is squared, you can never get a negative value. So 0 is the best thing, because if you make the smallest possible denominator, makes the biggest possible fraction, right? So what we do is I'm going to set, this is called electrical resonance frequency. This is a, I guess it's a circular frequency. All right. What you do is the best possible would be the biggest possible amplitude is 1 reactance, which is omega L minus 1 over omega C is equal to 0. Right? So from here, let's try to solve for omega. Right? I'm going to add, let's see, 1 over omega C. You get omega L is equal to 1 over omega C. Right? Then I'm going to multiply by omega and divide by L. So you have omega squared is equal to 1 over LC. right? Then we can just take the square root of both sides. So we have omega is equal to 1 over square root of LC, right? This is called the electrical resonance circular frequency because at this frequency, the amplitude of the steady periodic solution is the largest, right? When the reactance is equal to 0. All right, that's it. I hope that this was clear.